Let's get started. It's my pleasure to introduce today's speaker, Yeganeh Ali from Marshall School of Business. She'll be talking about how to measure differences in rankings.
Thank you so much. Thank you for having me. I know it's a Friday afternoon, and it's great to have some of you here even before the weekend starts. And today I'm talking about how to measure differences in rankings, and it's a data-driven version of a Mallows model. If you don't know Mallows model, I will talk about it later. This is joint work with Kiana Askari. She's now third-year PhD student at Stanford. And I just started at Marshall this semester. So it's great to be on this part of the campus. And I mean, it's lovely to see you all, and I hope to interact more with you as I'm working here. Let's get us started. So first of all, the main motivation of this talk was ranking chocolates for me, which as a chocolate lover. And what do I mean by it? So basically, I asked, the first time I was thinking about it, I had all of these different chocolates that I kind of like some of them and love the other ones. And I asked my friends to rank them, tell me which one is the best and which ones are the worst. And these are some samples that I got. And there are some similarities between them. All of them hated Hershey's, but about the best one, there were differences. And then the main question was if I get this kind of sample from you all and from Marshall and all, how can I make a central ranking of chocolates, the global ranking that what are the best chocolates in the world? So of course, chocolates are the most important ranking, but there are some other applications of it that we can think of. For example, there's voting application, especially in San Francisco area where I did my PhD, the city voting for different budgetary plans are based on rankings. And sports ranking, how can we gamble on a score of sports for the next season of football, for example, or recruitment for PhD students. Everybody has their own subjective ranking, but there are some internal rankings that we want to learn. And recommendation systems, when you go up on Amazon, yes?
So the criteria are also subjective when you don't know each other's criteria.
Yeah, so you're just getting some samples, and then the question is how can we infer a central consensus ranking? And can we explain the variabilities among these observed rankings? And the title of the talk, I said how to measure differences in rankings. You can see we have very different applications. And the question is how I'm penalizing a difference in chocolate. Is it going to be the same for voting in San Francisco, or should I think about it different? But I'd be more specific about that in a second. Because we want to explain some sort of variability and get a central ranking, we need a probabilistic method or model for different ranking structures. And let me first start with that. What are some common probabilistic models that people have looked about in ranking? The first thing is not even probabilistic. This is a very bored account. This is even a very naive version of aggregating ranking, which is just giving scores. So if, for example, you say Godiva is the best chocolate, give it the highest score, and then just decrease one score until you get to Hershey's, and then just sum them up to get their central ranking. Problem is you don't get the variability and differences, and you cannot generate from it, right? But another families of ranking, which is very common, especially in social choice, when people are explaining how people choose different ideas, is multinomial logic or Procalus. And in these models of ranking, we assume that every item has a latent variable theta I. And the way that rankings are generated are that the first item is sampled proportional to their scores, normalized by the sum of score. Then we throw that out, sample the next one similarly from the rest of the items until we get n different samples. This is a very it gives an intuitive understanding of how items what's the central ranking between them after we feed it to data. But there are some problems with it. One is it can overfit the data because every item has one parameter. The other one is that it dilutes ranking fast. what do I mean by it is that like I usually like choose chocolate over apple, but I also like choose chocolate over all fruits. But then if you're giving them each like different theta i's, like this probability is going to be like diluted as I increase the number of fruit options. But maybe I want a ranking model that I can basically see the correlations also as well. These are some models, like there are of course many more models, but yes.
What's theta I again? And what does J greater than I? Because you sign J after I, yes. What does that mean?
Oh yeah. So I mean that let's this is like each item is getting a score, theta I. And here I'm, for example, like giving you the probability that I rank theta 1 and then theta 2 and then theta up to theta n. The probability of choosing theta 1 in the first place is just like theta 1 over the sum of everything. And then that's now we put it out independently, choose the next one, like theta 2 over the sum of the rest of the equation. So, yes.
Sorry, the thing you mentioned about dilution,
Yeah.
is this supposed to mean like if every fruit has like theta i's at least some number, and if you have like
Yeah.
n of them, the probability that you get a fruit could be much larger than getting a chocolate.
Yeah. So if you look at the combination of all fruits, yeah.
So your notation pi means the theta 1 to theta n.
Yeah, but like let's not get to the detail of this model because this is not the final model. Like next slide is what I want to like get to the notation. This is the probabilistic model that I'm going to work with. It's all due to Mallows. It goes back to the 50s. And we are assuming that there is some central ranking. So like chocolate, some inherent ranking that we don't observe. And that's, I use the notation sigma. And there is a distance function d that any permutation pi that I observe, based on how far it is from this sigma, I'm going to like change the probability of it. So like, what do I mean? More specifically, the probability of observing some sample pi is proportional to the exponential of minus beta. Beta is just a temperature, like a dispersion parameter, times the distance of pi and the central ranking sigma. So the distance can be anything you want that you can like define on the space of all permutations. So these pi's are observed permutation and sigma is the inherent quality of chocolate, let's say. And beta is like controlling the concentration. Like the higher it is, it's just the samples that we see is like more similar to the central ranking sigma. When Mallows introduced it, he like used a specific distance function d, which was like the number of swaps you need to like get from sigma to pi. And that's called Kendall's Tau distance also, but I mean, I don't want to like get to the detail of it, but then like later, like in the 90s, it got generalized to like all right invariant distances. And today, like I'm going to focus on a specific family of distances, like I call them d alpha, which is, I'm looking at the difference between the ith element in the sample observation minus the ith element in the central ranking to the power alpha. And I sum them up.
I wonder if similar definition was appearing in exponential random graphs. You can look at exponential to some temperature and put some distance on some graph statistics.
Yeah. Like in there are models for it, right? Like for example, the number of triangles. Yes. Like it's a similar like exponential families of like what for permutation. Yeah. So like the special cases of this, for example, when alpha is 1 and 2 is very well studied. But let me like give one example of how this is computed, just to make sure we're all on the same page. So let's say we have these two permutations, and d2 of the distance of these two is just like look at each element and find the counterpart in the second permutation. So length is at ranking 1, and here is 3. So the difference is 2 to the power alpha, which is 2. Godiva is the same, so it's 0 to the power 2, and then for Ferrero is like 1 to the power 2 and so on. That's just like how it is computed. So I want you to remember the 3 parameters here, that beta is the dispersion, sigma is the central ranking, and alpha is controlling the distance. And what does it mean that like higher alpha? It means that we are penalizing more to like diverging from the central ranking. And lower alpha means that like I'm not like penalizing them. So for example, if you have a sports ranking and sigma is a true like strength of sports, higher alpha means that number 10 team has like a lower chance of like beating up number 1. But then lower alpha is like, it's more like random, like what happens as a result of the game. Yes.
So in this model, are we sort of assuming that we're weighting all of the distances between each pair equally? Like, is it possible, like, so if, for example, I really don't care between 3, 4, and 5, like, does this have like room to account for that, or?
Yeah, that's a great question. So you want to like add like some weight here. That's what you're saying. Yeah. Like right now, I'm not assuming to like add a weight. There are some studies about like the special cases of like when alpha is 1 and you add a weight, what happens? But it's still like there is no like good theory about it is all about how to estimate all of this. But it's a good question. Like look into. Yes.
Just a mathematical, I'm curious that you don't take the 1 over alpha outside.
Why don't I have the 1 over alpha?
Because this is d alpha is not a matrix. It's a
Yeah,
matrix.
yeah.
The triangle inequality fails. Yes, it's not a.
Yeah.
Just curious. I mean, for your purpose, probably doesn't matter that much.
Yeah, it didn't matter that much, but I just tried it, but it made my computation harder. Yeah. But it's a good thing to do. But in general, like I'm not introducing these distances into this because for special cases, as I said, like there is a body of literature for like 20 years that for the special case of alpha equal to 2, like how do you do estimation of beta? And I just like moved with that and like made it more general. It's like other alphas. Yes. But that was something I thought about. Yeah. Other questions about the model? Yeah, so as I said, this is like Mallows goes back to the 50s and the generalization goes back to 90s. So there is a lot of literature on it, especially that like even so like here like we have the probability being proportional to its exponents, but if you think about it, like the normalizing constant, I kind of removed it here. But even if you want to do sampling, it's not an easy problem because the normalizing constant doesn't have a closed form. And like one body of literature is just on sampling, like how do you do approximate sampling? And yeah, so like there is a lot of work for like the exact sampling and has closed form when we have a special case of distances, like the number of swaps. But for L1 and L2, so like when alpha is 1 and 2, we have approximate sampling based on MCMC and hit and run algorithms. And again, like for alpha 1 and 2, we have like a lot of results, especially more recently, like on ML community on using MLE, for example, for approximating the dispersion parameter and the central rank. With all of this, I come to the main question we are asking is that, do we actually have to assume what's the distance? Like, can we learn the distance parameter alpha as well as the central ranking sigma and the dispersion parameter beta all from data? So like, I want to like change the question of, well, like when we see the data, let's just assume one of these distances. Let's now also learn that. That's the main question. And I tell you the results informally first, and then when I get to it, like I'll be more formal. The main result is that yes, it's possible. We give a maximum likelihood estimation that jointly estimates all of the parameters of the model, and the estimators we can show is strongly consistent. As part of his MLE, we need to also like design a sampler from the Mallows model, because you'll see why in the next few minutes, but as we have to also like give a polynomial approximation scheme for sampling. So far, results for the sampling part is only for alpha greater than 1. But on the data, we use it also for your alpha too. We use some like variations with MCMC, and it was converging for the ones that we could compute the exact version as well. Any question on the high level results and question?
So alpha greater than or equal to 1, is it related to some convexity issue?
Yeah, like one part of it is not just convexity, it's just like how fast it decays, like the probabilities decays as they're when I get to the sampling part, it will be like I will like say more. But in general, like MCMC converges in theory, but then in practice it becomes like really bad, especially when alpha is like moving away from 0. So you can just use MCMC anyway when alpha is 1. Okay. If no more question, I want to like get to the MLE part first. Okay. So here's my assumption. I'm assuming that I have MIID samples from Mallows model with true parameters alpha 0, beta 0, sigma 0. And with any kind of estimation, the first sort of thing is to like write it.
You
like
mentioned 2 parameters, but actually there are 3.
Oh yeah, one is that, yes, so one is the dispersion, beta, sigma is the central ranking, and alpha is a distance. So yeah, there are 3 parameters. Yeah, maybe. Yeah, sorry for, I didn't realize I said 2, 3, yeah. And you just write the likelihood, like that's the first order thing to do. So if you, let's say I did it right, you can check it in 5 minutes or so, but there are like 2 parts to this likelihood. One is this Zn, which is the normalizing constant for a given parameter alpha and beta. Normalizing constant is independent of the sigma 0 because you can permute the matrices. And there is this sum overall observation of distances of the observed pi's and the central ranking that you're estimating. There are like some challenges with this likelihood that it's not convex in alpha, and they're like one of the parameters you're estimating is discrete, the other ones are continuous. It can get nasty if you try to like iterate over all of them. And but you can just like do a simple trick that I tell you next. The algorithm itself is like easy, but then like proving why it works is like the main challenge. So what's the algorithm? So this is the likelihood again. I reformulate it here. And the first step, I'm saying that let's just estimate the discrete parameter, which is the central ranking. So fix some alpha. Alpha was controlling a distance, or like how we are penalizing the permutation. Fix alpha to be, for example, 1. You can fix it to be something else. And then find the central ranking that minimizes the part of the likelihood that depends on it, which is like sum of the ones of the permutations observed, distance to the central rank. And this part of it is easy to like find because this translates to a matching problem. Like if you think about it a little, like maybe it is like 10, 15 minutes of your afternoon time, but that you can translate it into like a matching, like any, you have a bipartite graph that the weight between the ith node on one side and jth node is just the sum of all the like distances that it can have. Then the mean weight matching gives you the corresponding like permutation that like minimizes the likelihood.
So it's unique for sigma n.
Good question. We sure it's asymptotically unique. Yeah, but maybe not on a finite version, yes. And then we're saying, okay, now just fix the sigma m that you computed and solve it for the alpha and beta. Don't ever change the sigma m again. Now, yeah, and then maximize the likelihood to estimate alpha and beta. I say it like this is, I put like a star here because this is with a grain of salt. Like if you try to just maximize it, there are problems. You have to like change it a little bit to another root finding algorithm, which I don't get to the details. But I put you the form here just to say something, that the final function that they want to find is root. has some expectations of these distances over all possible permutation sample from Mallows. And computing this expectation needs you to either like have a closed form for the probability distribution or like have a sampling algorithm to basically estimate it. Otherwise, you can't just like do a root finding algorithm in this part. That's why we have to like later also like talk about sampling tests. But the overall like takeaway of this slide is like just separate the discrete from the continuous part. Questions so far?
How do you iterate? Then
This part is iterating. I like the root finding is true
then you
iteration.
estimate the new alpha and you
Yeah.
update it to get it. Do you change the sigma?
No, we don't change the sigma. Yeah, that was the first thing we did, and then it didn't converge. And we couldn't prove it's converging. Like we do the sigma once and we're done with it, but then like we iterate for alpha and beta. Like
And you
once
can
we-
prove strong consistency for sigma m
Yeah,
just by that fixing of
yeah,
equals one.
yeah. And I tell you why that with the next lemma. But like I wait if there are other questions here.
Yeah, but sorry, also the sigma is our like permutation at the center of our distribution, right?
Yes.
But isn't it also the thing we're trying to estimate in the end? Like, in the
Yeah.
end, we do want to rank it.
Yeah.
So I'm a little bit confused. So we're doing like, we fix the center and then we're just optimizing the alpha beta.
Yeah, I'm
No,
saying
it's-
that it's okay to estimate sigma m even with the wrong alpha, as long as you have enough samples, you correctly estimate that central rank.
I feel like if it's consistent, you should be consistent in any metric, so
Yeah.
it doesn't matter which alpha you choose.
Yeah,
But you
yeah.
might get a different speed of count.
Yeah, exactly. Like the rate of convergence depends on the alpha that you choose in the first round, but then all of them like it's just like consistent.
So you mean for arbitrary alpha, if you call the minimizer sigma alpha m,
Yeah, yeah.
m go to infinity, so
Yes.
limit does not depend on alpha.
Yes,
Is that what
that's
you
like, that's the next lemma that I had, but yeah, exactly. Yes, you.
Our goal is not just sigma, our goal is sigma alpha beta. We want all of them.
Yes,
I see.
yeah. But the main intuition is like, yeah, you said it very nice. That like if it's consistent in all metric, yeah. That's why it's okay to like guess it wrong. Which is like formalized in the next lemma that even though, so like let's say I have like guessed it wrong. So like my permutations come from alpha 0, beta 0, sigma 0, but I've guessed the alpha wrong. So it's like some red alpha here. If I want to minimize the distances with respect to like the samples I get, there is only one minimizer for this sigma. And that's that true sigma 0. This is basically saying that it doesn't matter how I'm like measuring the swap penalties of the chocolates, as long as I get like survey from all of the board, I eventually get to the true distribution. Okay. And then the main theorem, like the more formal version of it looks like this, that I have m IID samples from a true Mallows model with like 3 parameters, alpha 0, beta 0, sigma 0. As m goes to infinity, sigma m's converge to the sigma 0, and I have like CLT for the other 2 variables as well. So the previous result, and it usually looked at when alpha is equal to 1, let's like estimate beta and sigma, or when alpha was equal to 2. And they have like names, like the alpha equal to 1 is called Spearman's foot rule, and then the other one is Spearman tau, I think. Yes.
Yeah, so alphas and betas, are these real numbers or they're integers?
Oh, yeah, so they're real numbers between just
But
Every
the
function.
square root of n times like alpha m minus alpha 0, choose beta m minus beta 0.
Oh, no, this is not, this is a vector. I meant it's a vector. as a
Oh, okay,
vector,
it's
right?
okay, never mind.
Yeah,
Okay,
yeah,
gotcha.
yeah, sorry.
This-
No, it's okay. I should
Yeah,
like
it said
change
there's
my
identity, so I
notation.
wasn't sure, but
Yeah,
like
yeah.
maybe you could be.
No, I should change it. It's a good thing. I didn't think about it like that way, but
Yeah, there's covariance to it.
yeah, these are just like vectors. Yeah, yeah. So any questions so far? Otherwise, I want to like move.
I wonder how the proof goes for the CLT statement.
This part of it becomes like proving that let me go back. This function that we are like finding its root like through iteration, we have to prove that it's not convex, but we have to prove that it has like a unique root as like n goes to infinity. That becomes like the main thing. So like the main. So
Yeah, but if you want to prove a asymptotic normality.
yeah.
I have very limited knowledge of this, but what kind of big theorem you can apply?
Yeah, we're using like very classic theorems of this like root finding stuff, like for like sampling. It wasn't like really, this part of it wasn't like the main novelty. I mean, like we had to, the proof for this lemma was the main hard part to just like show that we can separate the two. Yeah. I have like 15 minutes, right? Like, let me get to the sampling a little bit and then I'd be happy to talk more about proofs. So the main goal in sampling, even like before generating samples, is first of all to approximate the normalizing constant. And I'm defining the notation z of n. N is the number of items, and of alpha and beta is just the sum of all these like weights that I'm putting into the permutation. And one simple observation in general is true about a lot of this normalizing constant is that like it can be written as a permanent of a matrix where aij is just the exponent of minus beta times I minus j to the power alpha. So if we actually use, you were asking like about why you didn't like use 1 over alpha power, then I couldn't use a theorem like that, like use it later. Yeah. And in general, so like I have basically a matrix that all of the entries are non-zero. And there is a famous MCSE algorithm, like Jerome Vigoda, like Sinclair, like going back to like 20 years ago, that you can approximate permanence and do sampling from any non-negative matrix. The theoretical convergence is n to the power 7, but in practice, it's even like worse than that, especially like if the weights are disproportionately like going to 0. So for that, we needed to actually, when we wanted to like use it, but then it didn't work on the larger alpha, so we had to change the algorithm, use the structure of the problem to do sampling. And it comes to a simple, like, it's like simple structure that we have to use that, like, because of this exponential factor, our matrix, like the matrix that we're looking at to find permanence, just goes to 0 as like we're going away from the main diagonal. Let's actually set these like entries that are log n away from the diagonal to 0. And we can show that now if I can compute the permanent of this new truncated version, then it's going to be like epsilon approximation of the whole matrix. And also like if I do sampling from it, it's like epsilon total variation distance. So we can just now focus on this banded matrix. And next I will tell you like how to do sampling from this banded matrix. Okay, this is just like explaining a little bit like why this decays. You can imagine why we can like do this truncation. It's because the probabilistic decay of swapping 1 just that goes exponentially to 0 because of the weights. Let me like skip the proof because I don't have a lot of time. But yeah, here I have like this banded matrix that I want to like compute this permanent actually exactly. And I do again, like I'm using like a few things that are equivalent. One is like matching can be like similar to permanence, and permanence similar to the Mallows model. And so like, let's say, for example, if delta is equal to 2, I can create a graph that one side of this bipartite graph is the rows, one side is columns. And then there is an edge if the corresponding entry of I and j is non-zero, and the weight of the edge is actually what's written there. Then when I look at the matching here, and I look at the product of it, that's going to be one term in the permanent. My goal is to compute the total matching sizes, but using the fact that every node is only like connected to delta nodes before and delta nodes after. So what I'm going to do next is to like use dynamic programming in a way that I start from one side of this bipartite graph, start matching it one by one, and I only have to keep track of the status of 2 delta nodes that are relevant for the next iteration. Let me be more specific with like an example. Like initially I start from node 1 and then I match node 1 and 2 and so on. And in every iteration, I'm keeping track of all the marginal weights I have seen so far. And that's one thing to keep track of. The second thing is the status of the nodes that are available for the next node to match. So here I show it with an example. Let's say I want to like match node I, and delta here is 2. So I have to keep track of 2 delta nodes that are relevant. So the ones that are shown with white is that they're matched before. So they're not anymore like possible to match them. And here there are like 2 possible nodes to match. And the third one, because that one was unreachable from I minus 1. So I don't have to even keep track. I know that's always like matchable because I keep matching from this side. How can I, let's say so far in my table, I said like the partial matching that reached this state for I is W. How can I update it for the next round? I look at all possible matchings for I. So let's say, for example, I is matched to this one, E1. Then I update the status of this node to be basically not available, and add E1 times W as the next next weight for the next row of the table. Then I do repeat this thing for the other matching. So if I get matched to this now, this node is unavailable, but this is still available. That's why this is the status I'm keeping track of. And if it's the third one, it's like the other thing. It's under this, yeah. So if I keep repeating this, I have like the marginal weights, marginal being just the sum of products up to like ith being like matched, plus the status. And the last row is going to give me the permanent of the matrix. The last row and last one of the status, like all of them are matched basically, is going to give me the permanent of the matrix. And you can reverse this whole thing to make sampling as well. Because if you think about it, like the one to the last row is like giving me the marginal probabilities if I divide them by the permanent that I've computed in the last row. So I can just sample the edges by reversing it. And then when I sample one, going to the next one is just the marginal condition on what I've already sampled. And by the end of like doing this whole like reverse version, like I have a matching that corresponds to a permutation. That's why it's like sampling permutations from this truncated probability. And the number of states that I have to keep track of, there are n different rows. In each of them, I have 2 to the power 2 delta states because there is a binary like 2 delta thing I'm keeping track of. So when the delta is log n, it's still polynomial. And in practice, it converges fast, which leads up to this theorem that like when alpha is greater than 1 and beta is non-negative, then we can give like a polynomial, like a PTAS, like polynomial-time approximation scheme for sampling from Mallows model and also like the
Has
partition
this
function.
sampling on this Bullock diagonal permanent has been studied before, or?
Yeah, yes. So like not for Mallows, but actually like there is this, it's called they have a name like it, but it's just start with T, and I don't know how to
Oh.
pronounce.
Oh.
Yeah, yeah. So like, but so like the matrix is that like basically the
The
diagonal.
Topless matrix.
Yeah, yeah, yeah. So like, how can you like compute the permanent for them? That's
Oh, yeah,
also-
it is a Topless
Yeah, yeah,
matrix.
yeah, yeah. So like, we just have to like change it for sampling, but it's the top.
I see.
Exactly, yeah. It's the Topless matrix, I think, is like the ith diagonal is like also equal
So
to
you
n
have
minus
n
I.
symbols that you put on those diagonals.
Yes, yeah. It's just-
But in that case, you don't have the delta parameter.
Yeah, it's a little different, but almost the same. Yes,
Okay.
Yeah, same idea. Good. And for alpha less than 1, that first like truncation is not even correct. Like you cannot truncate it by log n. That's why we can. If you like truncate it by log n, it's not like giving you a good approximation of the true matrix. That's why this proof doesn't work for alpha less than 1. But you can still use the MCMC. Any other questions from so far? Okay, if there are no questions, I just like want to like mention a little bit of empirics too. That one of these like data sets that we looked at was a sports ranking for American college football and basketball. These are like power ranking that are very subjective. Like people give different rankings of like how well a team is. Part of it is like who they beat, but also like their compositions of players and like who is like sick or not. And then we looked at the season from 2019 to 2021, use 80% of it for training and the rest for test. I don't want to like go over the detail of the result. We just have like our own results versus like our own model versus the Mallows when the distance is fixed to the Kendall's tau, and also Plack and Loose, which has had n parameters. The like Plack and Loose bits are in the in sample, but this is like the out of sample result that I'm showing you, so it doesn't generalize as well for out of sample. And this is for football. Similarly, we have it for basketball. But one thing I wanted to note here is like the estimated alpha. So alpha was the distance parameter. For basketball is almost 1. For football is 0.4. And this is like telling us something about a sport. So like the higher the alpha, it means it's like the sport is more of a skill game. The lower is like it's like more of a chance game. And then it's just saying like football like has more chance to it than like basketball. But one other interesting thing, I didn't put it in a paper, but there's like this old paper in 2010 that they looked at the data of poker versus like golf, and they said that poker has like more skills in it than golf. And we actually tested it out with this method too, and it also like gave the same result that like poker has like a higher alpha than golf. So like apparently, like I don't know, we should have it in Olympics maybe. Yeah, so like I was going reverse. Just like before finishing up, like I have some open questions that I think I'm interested in to look at. One is like mixture of this distance-based model. Mixture of Mallows model, like when we have like weights, for example, the question we have has been studied, and like this is like just sampling complexity of it is a area of research, especially in theory CS. But like, what if like the distances in each of them could be learned? Can we like work with the mixtures? And that's more relevant, especially when we have like recommendation system that like there are heterogeneous parameters like for each person, like you want to personalize it. The second thing is that these like fine tuning models that are coming up for LLMs, a lot of them are based on Bradley theory, which is another way of like preference data that like actually made GPT-4 to be like GPT-3 to be like so much better than GPT-2 was like using the human feedback into it. But there is a recent work of like actually using Mallows instead of Bradley theory is like basically pairwise distance. Using Mallow means that, for example, the dispersion parameter is telling us if you're asking a creative writing question from ChatGPT, this should have like a lower dispersion, and like if you're asking like a mathematical model and like you wanted more precise answer. So like that's something that we can learn from people's query. How can we use that like in generating next token and all? That's like a new area that like there are some work by Columbia folks, but I think it's something to like look more into it because their work doesn't like look at distance at all. It's mostly about how to use dispersion. Main takeaway is just that instead of assuming how ranking error should be penalized, learn the metric data, learn the metric from the data as well. And for finishing up, my research like is in general, if you see another talk from me, it usually has some graph network data, which wasn't the case for this. But my research in general is on learning and decision-making using structured data. Like there are 3 different areas that I'm trying to like connect. One is like algorithm design and probability inference and also like machine learning theory. One non-sponsored ad is that like I'm giving a talk in the theory seminar at CS like in November 13. That's like on a very different topic. It's on crowdsourcing for content moderation. If you're interested in like some more like CSC stuff, like I would be happy to see you there. And I'm in the bridge hall. If you want to talk about anything related research or just like come say hi. Bridge hall is next to the expo line. I don't know like if you all know. It's next to the basically the entrance of the expo line. And this is the QR code for the paper. And again, like thank you all for the having me.
Thank you. Any questions for the speaker?
Yes.
Someone going back to the future work. Just,
But I would like the questions.
yeah, open
Yes,
questions. One first thing I thought of is do you know, is there work also doing both of these at the same time, like mixture of distance for like fine tuning, like?
No, even just one distance and fine tuning that they haven't been worked. This paper, I can send it to you if you send me an email. It's just like fixing the distance, like how can we like learn the dispersion from the queries?
Yeah.
That already helped them.
I guess I was only thinking because of the, like, LLMs have like different applications usually, and you expect different
Yeah.
preferences, like maybe sometimes you want more factual information and sometimes you do want it to just
Yeah.
say something random. But also, can you talk a little bit more about like what you like are envisioning to add value from the alpha beta dispersion? Because for me at first, like I thought the main goal was to learn the ranking, so I got a little confused about like the ranking is like a simple procedure, and then we're getting more out of the alpha beta. For instance, like which sports are more like random versus like skill favored. Can you say like what you're envisioning like to add with the alpha beta to something like the mixture of distance or the fine tuning?
Yeah, to the fine tuning, I think the alpha is telling us basically like how the orderings matter. So let's say, for example, I'm asking for a recipe and then like it tells me like to cook before like cut. Maybe like that's not what I want. But if I'm asking like for just like what movies should I want? Like should I watch tonight? Then that ordering doesn't matter that much. So like that's like something about it. Beta is more like your example was very like good at like basically the precision of the answer. Like it's more about like creative writing versus math kind of question that you have. So like that's I think something even like for if you even fix alpha for just finding the beta here, this is the iClear paper, but they have a heuristic of like how to like predict beta from the queries, but I think there's more work to be done there. So like actually like have a more formalized version of just like trying out different algorithms. See. Yeah, if you're curious to like chat more, I'm like interested in this second area.
Yeah, I have a question about the estimating the central permutation.
Yeah.
So if you have a consistency, the natural question is, can I make any non-asymptotic estimate? So I want to find the estimator of this sigma.
Yeah.
That has a finite and convergence.
Yeah.
The bound, and the convergence should depend on this alpha and beta.
Yeah.
Would
We
that be
have a
possible?
convergence rate for alpha and beta, but it's terrible. Like it depends on n factorial. Like it's not, yeah, it's not the best convergence rate.
Well, my question is, if I just want an efficient estimator, find an efficient algorithm to find the estimator and
Yeah.
find a finite non-asymptotic convergence rate, is that
Yeah.
possible?
So like in like alpha equal to 1 was like what we saw to like work well in across data in practice, because while I showed you sport data, we also like tried it on movies and like news and all. But to give theoretical result, like what's the best like I don't have a theory result that like have both a upper one and lower one that are matching. I just have
For example,
like,
here
yeah.
you just use them matching
Yeah.
algorithm to come up with the estimator.
Yeah.
Maybe that's not the optimal in terms of the speed of convergence.
But the matching is giving us the best answer. Oops, sorry. It's giving us the best answer for that particular like distance.
But alpha equals 1.
For alpha equals 1, or like if even if alpha is different, but the main thing is that different alpha can have, for example, for some alpha we might have multiple answers. I don't see the here. Yes. Yeah, so like, I mean, yeah, I don't have a result to like show you what's the best alpha. I just like this alpha equals 1 was just like I'm trying on this data, honestly. That's so clear. But for example, for sport data, alpha was a little different. Like it was like 0.6 was better, for example, than 1, but 1 was a safe choice. Just, yeah. But I mean, I think it's a good thing to look at. Like,
Think any other questions? If not, let's take.
Well, I'll
Please.
say for others ask after.
Okay, thanks. Yeah, again.
thank you so much.